Okay, so first of all, I'm going to discuss a problem which has not been discussed earlier uh, because of some time constraint. And actually, I left the problem for you to solve, but probably you have solved. I don't know your status, but I think that most of you couldn't find a viable solution to the problem. And therefore, I thought this problem is so important that I need to discuss it. But if in the official class I discuss the problem, then it would just kill time, and therefore I would not be able to get chance of teaching you, would not get chance of moving further with the topics of vector space. So I have decided to discuss this particular problem first of all in the class, and for which actually I am going to write one result. I'm going to write one result which I can recall that I discussed in my last class, and I asked you if you have find if you can find time, you can prove this result, but otherwise you can avoid it. So I'm going to, probably you can, the result which I'm going to write, you can recognize it, but I'm not going to prove the result. I'm going to use it to do problems. Okay. So I'm just writing the result here. The result is taken from the exercise of spanning set, and the result is actually the question number 12 of the exercise. The result says that a subset W of a vector space V, of a vector space V, is a subspace of V, is a subspace of V if and only if span W equal to W. Span W is equal to W. If you want to ask me anything regarding during the class hours, so what you can do, you don't have to raise your hand, you just write in the chat box any question which comes to your mind during about the discussion of the topics. You can write in the chat box. I will check the checkbox for any queries, and I shall try to give the replies if I have the replies ready. So this is the result. The result is saying that you consider any vector space V, and you consider a subset of that. That subset will be a vector space. That subset will be a subspace if you can show that spanning set of W is exactly becomes equal to W. Don't have to write student ID. Do not write student ID in the chat box, because I'm not going to take the attendance. Please do not write student ID in the chat box. So you see, W is the subset. It will be subspace if spanning set of W becomes exactly equal to the W. Okay, so actually this set is also the spanning set. So I can write it as span of W. If you can show this, then we can say that W is the subspace of the vector space V. Otherwise, this result is very important in the sense that whenever we are supposed to show that a particular subset is a subspace, to show that a subset, a non-empty subset, is a subspace, we need to show what? Three different things. First of all, number one, the zero vector of the vector space belongs to W. Okay, let us name this subset as W. Number two, we need to show that X, Y belonging to W implies x plus y belongs to W. And number 3, we need to show that C belonging to W, C belonging to F, and X belonging to W implies Cx belongs to W. Now you see, these 3 properties need to be fulfilled if we want to show that a subset is a subspace. But if we have this result with us, then we will be spared of checking, we will be spared from checking these individual properties. Okay, so we can use this result to show that a particular subset is a subspace. Therefore, this result is very important. In a particular problem, I'm going to do not write student ID. I'm requesting. I'm not going to take any attendance for today's class. It is an unofficial class. Please do not write any student ID. So, I'm going to use this particular result in a problem, very interesting problem, very important problem in which I am going to use this particular result. Okay, so the problem is in chapter 2 of the book, you have this result with you that they solved it. We had a theorem like this, theorem 1.4, where it was written that any intersection of subspaces, any intersection of subspaces of V is a subspace of V, is a subspace of V. I'm not going to prove it though. Okay, so it is a result that has already been proved in the example section of the chapter. So what does it mean actually? Let us discuss geometrically. So we have suppose we have a vector space V, and suppose this is the subset W. Okay, not subset. Suppose W1 is the subspace. W1 is the subspace of V. Then we have W2. W2 is the subspace of V. Then we have W3. W3 is also a subspace of V, and so on. Okay, so we have W3 here. Now the result, the theorem says that any intersection of subspaces, that means if you consider W1 intersection W2, that will also be a subspace of V. Okay, if you consider W2 intersection W3, that is also a subspace of V. If you consider W1 intersection W2 intersection W3, that is also a subspace of V. If you consider in general W1 intersection W2 intersection ... intersection WK, that will also be a subspace of V. So any intersection will be a subspace of V. That is the theorem. This is the result the theorem is talking about. Okay. Now, this result has been, after proving this result, in the next paragraph, they have mentioned a very interesting point. The point they have made is that if W1 and W2 be two subspaces of a vector space V, then the result is W1 union W2 may not be a subspace of V. So this result is important. So W1 union W2 may not be a subspace of V. Sometimes it may be, sometimes it may not be. But it is not like the intersection, that the intersection is always a subspace of V. It is not like that. For some cases, W1 union W2 is a subspace of V. Or for some other cases, W1 union W2 is not a subspace of V. So we cannot say in general that the result is true always. When the result is true always, then we prove it, just like the theorem 1.5 has been proved in the book. But if the result is not true always, That means there are some counter examples for which the result is not actually, the result is actually, I mean, W1, I have to show that there exists two subspaces W1 and W2 for which this result is true. I mean, W1 union W2 is not a subspace. I have to show it by a counter example. So when you want to prove something, you have to prove it in a general way. You do not have to show any example, but if you want to disprove something, then you have to show one counter example. At least one counter example will be important. It will be sufficient to show that the result actually is being violated in general. So here I'm going to show you that counter example. So therefore this problem is important and interesting, and this problem is also very important for gate examination. So proof. I mean, I shouldn't write proof. I have to actually I have to write solution, because I'm not going to prove it. I'm going to show the counter example. We know that R2 is the set containing all ordered pair of points where we have this. So it represents all 2D points. R2 represents all 2D points. Okay. And from there, I'm going to select what is R2. Let us draw it diagrammatically. This is your R2. Okay, this is the origin, and this is the y-axis positive direction. This is the y-axis negative direction. This is x-axis positive direction. That is x-axis negative direction. You can consider, you can draw a coordinate axis on your mobile screen or laptop screen at the middle, and you can divide your entire screen into 4 halves. That will be your 2-dimensional space. I'm just drawing a part. So this is what is represented by R2. Okay. Now in this R2, I am now going to consider 2 subsets. What are they? Let us consider 2 subsets W1 and W2 of R2. Okay. Now, what are these subset? Let us define it mathematically. First of all, subset is W1 is given by x0, x belonging to R, and 0 is the real number, you all know. So actually I'm considering this part, I mean this positive x-axis. Okay, positive or negative or whatever. I mean x-axis, I'm considering x-axis by this. So it is what? This is actually the x-axis where y coordinate is 0. And W2 is given by the points, set of points 0, y, where y belonging to R. So it is represented by y-axis. Okay. So we have this. This is your, this entire thing is your W2. I have to bold this portion also. So obviously you see this is a subset of R2, and that is also a subset of R2. Now I want to prove first of all we need to prove that W1 and W2 are subspaces of R2. Now to prove subspaces of R2, if I go by this rule, I need to show for individual cases, means for W1 and W2, that these results hold. So I have to show this for twice. That means if you consider the properties individually, I have to consider 6 properties. 1, 2, 3, again 1, 2, 3, 6 properties. Okay, twice actually. So it will be a hard-working job. Okay, it will be a time-taking job. So we have to find some easy method to solve that particular subspace subset is a subspace. So I'm going to use this result in the given problem. So I'm going to use spend W equal to W, that result, to show that W1 is a subspace of R2 and W2 is a subspace of R2. Now what is spend W? Spend W1. Spanning set of W1 means that what is the definition of spanning set? All possible linear combinations of the set. All possible linear combinations of the set, that is called the spanning set. So by definition, it would be like this. And small a is any scalar quantity. So small a is also any real number. And therefore, this can be written as by scalar multiplication of the ordered pair. We can write it as ax0, x belonging to R, a belonging to R. Okay, or you can write it as some other coordinate x prime 0, x prime belonging to R, a belonging to R, and where x prime is equal to ax. So when we multiply, in the last class I told you that when we multiply something by a scalar quantity, that means the thing is actually getting elongated or contracted depending upon whether small a is positive or negative, and it remains same. It becomes 0, 0, 0 if a equal to 0. So actually you see that the points, x prime is also an arbitrary point. You have got an arbitrary point on the x-axis. Okay, and for different values of a, positive, negative, 0 values of a, you are actually getting entire x-axis once again. So the span of W1 is actually equal to W1. The spanning set of W1 is equal to W1, and which implies that W1 is a subspace of R2. So you see how easily we can show that this is a subspace of R2 by using that beautiful result. Okay, we don't have to check the individual points though. Okay. In a similar manner, if we write span of W2, then by definition this is all possible linear combinations of the points present in W2. So I can consider these points. I can consider these points y belonging to R and b belongs to R. Okay, and that is equal to, you see, 0 comma by, where y belonging to R and b belonging to R, where okay, let me write it in this manner, and this is equal to, we can write it by any arbitrary coordinate y prime, where y prime belonging to R, b belonging to R, and y prime is equal to by. Okay, so span W is also, you see, y prime being an arbitrary coordinate of the y-axis. So it is actually, what is that? It is actually getting elongated or contracted depending upon the sign of the scalar quantity b, and therefore this is nothing but equal to W2. So by this, we are easy to show that it is very easy to show that W2 is a subspace of R2. So we have considered two subspaces. One is called W1 and another is called W2 from the set R2. Okay, then these are the subspaces. We have already proved it. Let us now select the union of these two sets, W1 union W2, which is actually given by this x belonging to R union 0y, where y belonging to R. So we have considered the union of these two sets. So we are going to prove, to show that W1 union W2, I shouldn't write the word to show. To check that, I must write the word check. To check whether that W1 union W is a subspace or not. Subspace or not. That I want to check. Okay. Now you see, first of all, here I'm going to use the result span W equal to W once again. So if I want to use this result, span W equal to W, so what I find? So let us write it. Span of W1 union W2, that is all possible linear combination of the points present in W1 and W2. So I am going to write it as AX0 plus B. Let us write some other scalar number. Let us denote scalars by some other symbols just to distinguish. Otherwise, you may think that this B and that B are same. So A prime into X0 plus B prime into 0Y. Okay. And where A prime, B prime belonging to R, X comma Y belonging to R. So that is the definition. That is the result of that is what I am getting by using the definition of span of W1 union W2. So if I do the scalar multiplication and coordinate wise addition, what I get, let us see. We get A prime X0 plus 0 B prime Y prime, where A prime, B prime, X prime, sorry, not X prime, X comma Y belonging to R, and this becomes A prime X 0, sorry, A prime X plus 0, 0 plus B prime Y prime, okay, and A prime, B prime, X, Y belonging to R, okay. So in this manner, ultimately what we get A prime X comma B prime Y prime. This should not be this should not be Y prime. Let us write it properly. B prime Y. Okay, I have B prime Y. That will be B prime Y. Here also this should not be equal to, let me rectify it, and here also that. So A prime X comma B prime Y, where A prime, B prime, X, Y belonging to R. Okay, so we have got this, and we can denote this by any arbitrary symbol. We can write, in place of A prime X, we can write X double prime. In place of B prime Y, we can write Y double prime. Arbitrary coordinates. I'm just denoting this. It's just a matter of notation. So A prime, B prime, X prime, double prime, Y double prime, these all are real numbers, and A prime X is actually my X double prime, and Y double prime is my B prime Y. Okay, so we have got this. Now you see that when I consider this span of W1 union W2, what we get? We actually getting this coordinate. Span of W1 is equal to this. Span of W1 union W2 becoming this coordinate, and this coordinate, this X prime, X double prime, and Y double prime can be anything on this two-dimensional axis. But obviously that is not equal to W1 union W2. That is not equal to W1 union W2, because since X double prime and Y double prime are arbitrary coordinates, okay, so it doesn't, arbitrary coordinates. So not all the points of the form x double prime y double prime are in W1 union W2. W1 union W2 only contains x and y axis, and therefore span of W1 union W2 is not equal to W1 union W2, and this implies W1 union W2 is not a subspace with respect to the example chosen. This is not the only example. Many other examples are there. I could think of only this. So you can think of some other examples where W1 union W2 is not a subspace, and therefore W1 union W2 is not a subspace in general. May not be a subspace in general. And by geometrically, we can also understand this particular thing. So suppose if you want to understand this thing geometrically, so let us only consider the positive quadrant. So suppose this is my, for our understanding, suppose this is my W1. I'm taking the positive axis only, and that is my W2. So I'm taking the negative x only. So here I'm going to set one point, that is I mean, this point is having coordinate x coordinate 0, and this point is having x coordinate 0, y coordinate 0. If I join them, you see these points lying on this particular line, they are not the member of W1 union W2. They fall outside this. My W1 union W2 consists of only this part and that part. From pedagogical point of view, I am taking the positive direction only. So therefore, geometrically, it also shows that the 2 points are not, these two things are not, the union of these two are not subspaces, which proves our required result. Okay, understood? So this the result you always try to remember. This is very important, that W1 union W2 may not be a subspace of the vector space V. Now, since suppose when now the important point which I want to make over here, important note, is that when we talked about set, when we consider two sets, capital A and capital B, what do we study? We study the set operations. Okay, and the useful set operations are A intersection B, and we can study A union B. A intersection B means, you know, that we have two sets, capital A and capital B, and A intersection B is the common region between these two, common points lying on both A and B. Yeah, I'm going to show the previous slide. Okay, I will come back to the previous slide, don't worry. I will come back. I will write something over here. Okay, so then you can check, you can write what you have missed. Okay, so A intersection B means this common part, and or we can talk about this thing, which is, you all very well know, that A union B. Now, what is A union B? A union B means the combine. I am combining the two sets. By A union B, I am combining the two sets. Very carefully listen to me. Very interesting point, also can be useful in gate examination. So when A union B, I am combining the two sets. Okay. So A union, the operation union helps us to combine the two sets. Okay, so when we talk about subspaces, subspaces W1 and W2, then W1 and W2 are subspaces, then to combine the two subspaces, to get a bigger subspace, we cannot use the union operation. To combine them, because we have already proved that the union of two subspace may not be a subspace. So how can we combine them together? To combine, if we are talking about, if you are interested about subspaces and not just sets, to combine subspaces together, W1 and W2 together, we need to use the operation W1 plus W2. And you already know that what W1 plus W2 is. It is given in your book. It's called linear sum. So I'm just writing for the sake of completeness of this particular discussion. So W1 union W2 is given by this particular definition. So you may think that why W1 plus W2 is needed. I mean, why do we want to study W1 plus W2? So this is because we always want to combine two different systems together. When it is a matter of set, then we combine them using union operation. But if it is a matter of subspace, then the subspace is designed in such a way, the definition is designed in such a way, it says that W1 union W2 may not be a good operation to combine the two subspaces, because W1 union W2 is not always a subspace. So there must be some rule by which two subspaces can be combined, and the rule is W1 plus W2. And if we along with this, if we can show that W1 intersection W2 contains the zero vector, then together we call this as direct sum of W1 and W2. Direct sum of W1 and W2. So that here I have discussed what is the purpose of actually bringing this particular operation into the picture. We knew that A plus B, two sets, we cannot add two sets. I mean, there is no meaning in adding two sets, A and B. So, but W1 and W2 being two sets, they are added. So what is the purpose? Vector addition and linear addition. Vector addition means, you see the addition here, actually someone has written vector addition and linear addition. Vector addition is means if you consider X individually, X is a vector, Y is a vector, so actually we are adding them together. Vector addition is what? We are adding these two vectors X and Y, because X is a vector and Y is a vector, because X is a member of W1 and Y is a member of W1, and W1 and W2 are subspaces, means they are vector spaces. The thing is actually called linear sum. It is because all the powers of X and Y in this sum are 1. So therefore it is called linear sum. You cannot get a term like x square plus y square or x cube plus y like this. So this is called linear sum, and therefore since we are dealing with linear sums, therefore this is a matter of all these matters are actually belonging to the topic of linear algebra. Therefore it is called linear algebra. Okay, so vectors, we are adding two vectors, so it is a vector addition. We'll have to add with respect to the vector addition rule. But sum is called linear sum is because the powers of the variables present are 1, power 1. But then the scientists or mathematicians thought that if W1 and W2, are not always a subspace of V, then when can it be a subspace of V? So therefore, they actually found this, that when W1 and W2 are two subspaces of a vector space V, then W1 union W2 is a subspace of V if and only if W1 is contained in W2 or W2 is contained in W1. I am leaving this proof for you to solve. This is your, this is your homework, and this is this particular problem is actually given in the exercise 19 of the book. Okay, so you see, if you can actually show that, okay, this is your V and that is your say W1, and suppose this part is your W2, then only W1 union W2 will be a subspace. W1 union W2 in this case will be actually equal to W1. Very easy to show this. When one is contained in the other, okay, when W2 is contained in W1, so W1 union W2 will be equal to W1. And if W2 contains W1, then in this case W1 union W2 will be exactly equal to W2. So obviously, then this result is a trivial result. I mean, this result is important in the sense that, okay, we have got some kind of condition under which the thing will become a subspace, but this condition is not very important in the sense that we have got condition, but it is pretty obvious. You can very easily solve it. Okay, so this is the only condition under which the two subspaces, union of two subspaces, will be a subspace. Otherwise, there may be some cases, as I have discussed, the thing may not be a subspace. And to combine two subspaces together, we have got this operation linear sum, and therefore this operation linear sum is very important. This is the first problem which I wanted to discuss with you. And with this particular problem, I have also showed you how to apply the result spend W equal to W to prove that W is a subspace. So you have got two different things. You have got to see two different results here. Okay. Another interesting point which I want to make a question. First of all, let us put it in the form of a question, that, and every example which I am taking right now from this book, which I have with me, that is the soft copy of the book is available with you. It's Friedberg linear algebra. So the discussion, I'm taking the exercise. Actually, last night I scanned the exercises and I actually selected a few problems for you too, which I thought that it would be important to discuss the problems with you. Okay, so the important point I'm going to make from this is this. We know, let us put the question in this manner. Can a vector space have two different spanning sets? What do you think? Can a vector space have two different spanning sets? In the last class, we showed that if I consider the vector space R2, I showed that, if I consider the vector space R2, the set of all ordered pair of real numbers, xy belonging to R, and if we consider a set of this form, containing the points 1, 0 and 0, 1, then we know that this set spans R2. Span of S is equal to your vector space R2. Okay. Now this becomes one spanning set. Similarly for R3, X, Y and Z belonging to R3, where X, Y, Z are real numbers. And if we can consider the set S is equal to as 1, 0, 0, 0, 1, 0, 0, 0, 1, then this we can also show that, let us name it as S1, let us name it as S2, and I have shown that S span of S2 is actually equal to R2. Fine. So my question is, can a vector space have two different spanning sets? Yes, spanning sets are generators. Someone has written something in the comment box. You all can see there. It's his comment. Spanning sets are generators, as these sets generate entire vector space. Okay, spanning sets are generators. Can we have different spanning sets? So I'm going to discuss this with you right now. So we have a problem given in question number 6. Let us go to the next page, so that because I shall not be able to finish the problem in this particular page. Or okay, I can write the question over here. The question is given in someone has written something. Oh yeah, sure. These are printing mistakes. Okay, yes, right. R3. Obviously it will be R3. Now the question number 6 is, show that the vectors one, 1, 0, 1, 0, 1, 0, 1, 1 generates F3. We already know that 1, 0, 0, 0, 1, 0, 0, 0, 1 generates F3. F is a field. In place of F you can consider R. In general it generates F3. So the problem says that prove that this result also generates F3. Okay, so let us try to prove it. Solution: for the set 1, 1, 0, 1, 0, 1, 0, 1, 1, we have to consider three scalar quantities A1, A2, A3 in the field F on which F3 is the vector space. Now if you want to generate, okay, so let us select let us select 2 points, let us select a point, an arbitrary point from let us select an arbitrary point from the vector space, F3. Let us select an arbitrary point from the vector space F3 and let it be x, y, z, x, y, z. So we want to check that with respect to the parity. We can consider this to be x, y, z, or whatever point you can consider. X, y, z are actually the members of X. X, y, z are belonging to the field actually. Okay. We want to check whether this can be expressed in terms of as a linear combination of these vectors or not. So with respect to these scalar quantities, let us express this triplet x, y, z as a1 into 1, 1, 0 plus a2 into 1, 0, 1 plus a3 into 0, 1, 1. Okay, I want to find these scalars. Our objective is to find these scalars. There must be some what are the form of these scalars for which x, y, z can be written in terms of linear combination of these three triplets. Okay, so let us try to do it. So x, y, z, this will be equal to a1 0 plus a2 0 a2 plus 0 a3 a3. This will be equal to x, y, z, which is a1 plus a2. The next one will be a1 plus a3. Next one will be a2 plus a3. Okay, and from this, this is a triplet, if I compare these two sides, the first coordinate will be associated with the first coordinate, second coordinate will be associated with the second coordinate on the left hand side, and the third coordinate will be associated with the third coordinate on the left hand side. So we are getting three equations. We are getting 3 equations, 3 unknowns. So we are going to solve it. We are going to solve these 3 equations and 3 unknowns, and we need to find the values of a1, a2, and a3 in terms of x, y, z. Because x, y, z is a general point, so the result will come in terms of x, y, z. Okay, so let us try to prove it. So let us name these equations. Let this equation be A, this equation be B, this equation be C. So if I subtract the equation B from equation A, we get a1 plus a2 minus a1 plus a3, and that will be equal to x minus y. This implies a2 plus a3, sorry, a2 minus a3 is equal to x minus y. You can name this equation as D. Below D, we can put a2 plus a3 equal to z. Okay, and then we can subtract first. We can add first, plus let us add the 2 equations. So we'll get 2a2, which will be equal to x minus y plus z. and therefore A2 will be x minus y plus z by 2. Okay, so we have got A2. Next, we can subtract the thing. So so we can add the two equations, and this equation is your equation C. So we can add the two. We have subtract one equation from the other, so we can subtract C, D from C, and that will imply 2A3 is equal to z minus x plus y, and therefore A3 will be equal to z minus x plus y by 2. Yeah, well, someone has written this, Aditi Das has written, sir, add all the equations and then subtract each one from the total. Yeah, you can also do so, whatever. Anything you want to. 3 equations, 3 unknowns, no problems, solution will be unique, that's it. Okay, and lastly, so Aditi, you tell me what will be the value of A1? We have got A3 and A2. So what will be the value of A1? Can you tell me? We have got A2 as this. This is my A2. This is my A3. Now you can use this in any equation. You can put the value of A2. You can substitute the value of A2 in here in this equation, and you can get A1. So what will be that? Anybody? Okay. Someone has written x plus y minus here. X plus y minus z by 2. So ultimately in the next page, I'm going to write all the value, the points, the variables. So what we have got? So we have got that the arbitrary point x comma y comma z in R3, sorry, not in R3, let's shouldn't write R3, in F3 is expressed as x comma y comma z is equal to, so we had x plus y minus z by 2. X plus y minus z by 2 into, what was the point? 110. So we can write 110. Okay, then plus, next point is A2. A2 is x plus z minus y by 2. X plus z minus y by 2, and that is into 101. So we write 101 plus the last point is z minus x plus y plus z minus x by 2, y plus z minus x by 2 into 0, 1, 1. So we see that we have successfully represented the arbitrary vector xyz in F3 with respect to the vectors as linear combination of these 3 vectors. Okay, so the result is span of this set 1, 1, 0, 1, 0, 1, 0, 1, 1. The spanning of this set is actually equal to F3. Okay, so 1, 1, 0, 1, 0, 1, 0, 1, 1 can span F3. Okay, so if you are now asked, the question will be set in the gate in the following manner. The question will be set in the following manner. So what will be the gate problem? The gate problem will be like this. Which of the following can be spanning set or sets of F3? We have been given an option like 1 1 0, 1 1 1, 1 0 1. Number 2 is 1 1 0, 1 0 1, 0 1 1, and number 3 is 1 0 0, 0 1 0, 0 0 1, and number 4 all of them, number 5 only 2 and 3. So this can be the question in the gate. Now you see, the if this is the question, then we do not know about this set. We have to check whether this is the spanning set or not. Okay, if we can find that this is also a spanning set, the answer will be all of them. If but we already know about this set and that set. So if you tick only this, that means you are actually avoiding that. And if you only tick this, then that means you are actually avoiding that. So in that case, we have to tick on question number 5, option number 5, which says, sorry, I shouldn't write only, both. I must use both 1 and 2. Okay, then it is all of them. Then it is all of them. But sometimes when we give this type of thing in the problem, my voice is breaking because there was kind of internet problem from my end. So just hold on, it will be rectified. So often students think that, sir, I have ticked in this option, but this is an option. I have ticked only this option too. This is an option. So why shouldn't I get full marks? The answer is, yeah, that you shouldn't, you will not get full marks, because when you are taking this option, that means what? That means the examiner thought that you are sure about this result. I mean only, but you are not sure about this too, and therefore you will not get full marks. You have to check each one of them. So therefore you have to tick on, as someone has written that he has checked, this is also a spanning set, probably he has checked. So you have to tick on all of them. If you find these two only, then you have to tick option both 2 and 3. So therefore this result which I have shown you, which I have proved just now, or solved just now, is very important. The ultimate result is a vector space can have more than one spanning sets. Okay. So you remember this result. You remember this particular result. Now I'm going to stop the share and I'm going to move on to, I'm going to present the book of Friedberg, and I'm going to read something from there. So let us do it. So actually you see, Actually, see, I have solved this particular problem. Question number 6. Question number 6. This problem is I have solved, and all these problems which you can see, see over here, that all these problems are very important. Okay, say PNF is the vector space over PNF is the vector space of all polynomials of degree lesser than or equal to n. It is a subspace of PF actually. So it is actually the generator of PNF is actually 1 x dot 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 x to the power n. I mean, if you do not have these elements 1 x to the power n, these elements are vectors actually, and these, if these are not present, you cannot generate any polynomial. We generate polynomial with these terms. So this is the generator of PNF actually. Remember, this is very important. Okay, now let us move on to something else. So you are supposed to don't write your student ID. Your student IDs are not important for today's class. Only if you are present, that is all for me. Okay, so I'm not actually taking any attendance. After this, you come to this section. I am leaving other problems for you to study. I am leaving other problems of the exercise for you to study. So you keep on thinking and try to find out the solutions if you have time. So let us move on to the next topic. It is called linear dependence and linear independence. As I said, now all the linear dependence and linear independence. Before we started with vector space, then subspace and spanning set and linear combination wasn't there in the syllabus. Now linear dependence was there in vector space section, linear independence was there in the matrix section, but both of them are connected. You see, one is complementary to one another, complementary to other. So I do not know if a syllabus setter is writing linear dependence, the term linear dependence in vector space section, why isn't he mentioning linear independence over there? I don't think he has to write linear dependence and linear independence of vectors. So let us now read it. Okay, let us make this maths class a little bit of history class, and let us read these lines to understand what is there. Suppose that V is a vector space over an infinite field. You, Nihal, exit and rejoin. Probably the solution, the thing will be solved, because I have the network connection. My network connection is good. No trouble from my end. You exit and rejoin. If everybody is having this particular problem, then you tell me. Otherwise, if this problem is only with Nihal, then okay, then you have to exit and rejoin. Now suppose that if V is a vector space over an infinite field and W is a subspace of V. Okay, then all of you exit and rejoin. I am also actually closing this session, and I am also trying to rejoin once again. Just hold on a minute. Okay. Ayush Pandey, yeah, okay.